Good morning. My name is Jacob Watkins, and I'm a quantum algorithms researcher at JPMorgan Chase. Today I'm going to tell you about this work that I did with my collaborator, James Watson, on improving product formula calculations using classical extrapolation techniques, particularly for the task of time-evolved expectation values. This is based on a collection of two works. I'll be focused primarily on the first one. You can see the two archive codes up there. The first one is based on regular deterministic product formulas. My collaborator, James, has done some excellent follow-up work on randomized product formulas. I'll talk a little bit about that at the end. But if you're interested, I encourage you to have a look at that as well. I'll do this talk in two parts. The first part will be a bit of a high-level overview containing most of the essential aspects. For many of you, this might be the most important part to listen to. In the second part, I'll come back around and try to fill in some of the mathematical details. Please have a look at the paper if you're interested in more of those details, or ask me a question at the end. So in this first part, I'll give an overview of the idea of Trotter extrapolation and Trotter error mitigation. I'll talk about some prior work in this area, and then discuss how this work changes the situation on this topic. So previously, I had the pleasure of giving a very similar talk at the first QSim conference in Telluride, Colorado. Very, very lovely setting. A little different from New York City, but they both have their merits. And so this was work that was done alongside Gumara Rendon and Nathan Wiebe. And we introduced an algorithm for improving both eigenvalue calculations and time-evolved expectation values using a polynomial interpolation technique with robustness to error guaranteed by the use of Chebyshev nodes for the interpolation. So I'll give a bit of a high-level overview of this technique, but I'll describe it in more general language that suggests somewhat of a more general approach that you could take for these sorts of extrapolation techniques. So the idea is we have some product formula P that we're going to use to do some dynamical simulation. And regardless of which formula we choose, there is some accuracy parameter at play. This parameter S, concretely, it is 1 over the number of Trotter steps. We can sort of mathematically relax this a little bit, as we'll do a little bit later. But the point is, for small values of S, we have very good accurate values. And we would like to get as close to S equals 0, corresponding to the ideal evolution, as possible. Rather than take the smallest possible value of S, as we might naively do, the idea here is we will take different values of S according to some scheme. And in this process, we'll learn some more information about the relationship between our quantity F of interest. It could be an expectation value, could be an energy eigenvalue, and this parameter S. And with this data that we've collected, we're going to then do some classical numerical scheme to estimate F of 0. So let me illustrate this a little bit more concretely with the polynomial interpolation technique. So suppose we're interested in time-evolved expectation values. So we have some observable A, which is evolved for time capital T according to some product formula with some accuracy parameter S, again, thinking of it as just the inverse Trotter step. And we plot this with respect to the parameter S. And for sake of illustration, imagine that the functional form looks something like this. I've sort of just drawn this picture, nothing, not implying any particular behavior. But on the horizontal line, the dashed line, this is the value we're interested in. It's the exact time-evolved expectation value. So the idea is we're first going to choose some scale around for S. It's going to depend on the hardness of our simulation, the length of simulation, size of our system, so on. As the problem gets harder, we will naturally need to shrink this interval to be able to have reasonably accurate information about the actual value. We then do the quantum part of our calculation. Namely, for various values of S, in this case, chosen somewhat to suggest a Chebyshev interpolation, as we will do. We estimate f of s. Note that even for non-zero s, we still have only the ability to estimate f due to whatever measurement protocol we're using. Perhaps there is some physical error in the simulation. But regardless, there's some sort of irremovable error here. We then do some extrapolation scheme, in this case, a polynomial interpolation. I sort of interchange interpolation, extrapolation, because the idea, regardless, is we're going to move towards small values of s given information about large values of s. And we're going to then take, in this case, as our estimator, the value of this polynomial pf at s equals 0. A couple of comments. You'll notice I'm playing a little maybe fast and loose with s. I said it was 1 over the number of Trotter steps. We can formally extend to real values using fractional queries. Whether or not we actually want to implement these algorithmically for the time being, we can at least mathematically consider them. And negative values of s simply correspond to an inverse product formula, which, given as a quantum circuit, we can do the appropriate reversals and produce that. So one natural question might be why one would be interested in doing this approach. We have many sort of highly accurate simulation schemes, even moving beyond Trotter, and so on. But for the sake of this discussion, let's focus maybe on Trotter schemes and think about perhaps an alternative, which would be using a high-order product formula if we really needed very high accuracy simulations. One unfortunate barrier to the use of these formulas is that they have an exponentially increasing number of terms as we increase the order of our approximation. So there exists sort of arbitrary order formulas. However, they, unless our accuracy constraints are very severe, this is extremely expensive. Whereas, and I sort of have to maybe tell you some things without full justification here, but basically because each of our data points is not severely close with each data point to the origin, we have roughly the same order of magnitude of Trotter steps for each data point. So we're slightly greater than linear in the number of factors we need to take in order to achieve sort of a given order of an approximation. Even so, even if we do a high order formula, we still get something like inverse precision to the 1 over p for some fixed p. Whereas for fixed product formula, we can get polylogarithmic scaling using these extrapolation procedures. The degree of this polylog is not so severe. Depending on the method you use, it could be 2 or 3. This may even may be reduced in practice or theoretically. On the other hand, when we're doing these extrapolation schemes, we're not producing sort of a high fidelity representation of the density matrix of our state. We are simply calculating some classical quantity, such as an observable expectation value. And so it's possible that these techniques are limited in certain ways. We can't always push the state further along to further quantum processing down the road. So there's some trade-off with maybe generality, but for the tasks that we're interested in, this can correspond to some significant benefits. Right, so there's some prior work on this topic, although it's perhaps not so old. The first work that I'm aware of that suggested very concretely using a Richardson extrapolation technique for these sorts of expectation value tasks comes from a paper from Endo et al. And so there's several works on using this for observables. There's another more recent work from a group out of IBM who were able to actually do some of these Richardson techniques on actual hardware and observe some improvements in those calculations. These works are accompanied by some mathematics, but there is still left the question of rigorous scaling and asymptotic and analysis that leaves room to be filled in. I already mentioned the polynomial interpolation method. We did provide rigorous query complexity scaling there. But focusing on the expectation value calculation, we were not able to get sort of exactly the results we wanted or expected, even though we showed sort of the reductions in Trotter error, leading to better scaling in epsilon to approach Heisenberg limited precision. Our scaling with simulation time, capital T, is quadratic regardless of the order of the formula. In contrast, for higher order regular Trotter, you get something like t to the 1 plus 1 over p. So as you increase your formula degree, you get closer and closer to linear scaling, which is the optimal. Furthermore, our method required fractional queries because you need to basically do this interpolation scheme that is not exactly corresponding to integer Trotter values, and this requires some additional overhead and makes the method slightly less natural. I should mention that there's recent excellent work by Gomara Rendon that also sort of alleviates this fractional query technique by using integer values of a Trotter step and then doing basically another interpolation on top to get the Chebyshev nodes that you need. And this is sort of needed to exactly approach the optimal Chebyshev interpolation. So what does this work do in light of all these previous works? It's really kind of a mix of several different advances. One thing that we do is we sort of unify the approach of Trotter error mitigation. We combine the Richardson and polynomial interpolation methods under sort of a unified analysis, specifically for expectation values. We derive a very concrete error series and show how these methods cancel order by order. And we bound the norm of this series in order to get a very concrete representation of the error in these methods. And besides rigorously analyzing these very concrete methods, it suggests a way of analyzing other possible extrapolation techniques that aren't considered here. We additionally simplify the polynomial interpolation algorithm, removing the need for fractional queries. We basically do this by using some results from pure mathematics, which suggest maybe what you would expect, which is that if you do an approximate Chebyshev interpolation and you want to know if that numerical procedure is well conditioned, it turns out the answer is yes, and sufficiently so that it doesn't really affect your scaling too much in your procedure. We provide the expected commutator scaling, the proof of which is more complicated than we had imagined. But it's certainly to be expected. We are just doing some Trotter calculations on top of some classical numerical procedure. So the commutator is not exactly the same as you get from regular Trotter, but they are related in certain regimes. And in any case, the commutator is always bounded by a sort of a one norm scaling. And finally, penultimately, we get a improvement in T to match regular Trotter. And our expanded analysis includes not just coherent Heisenberg limited measurements, but also just shot noise procedures. And in both frameworks, we analyze the total runtime and the maximum circuit depth. These two figures of merit are useful, on the one hand, for maybe fault-tolerant quantum computers with indefinite runtime. And on the other hand, for circuit depths, these are still really important when considering hardware today, though it's constantly improving. OK? Well, so I think given constraints of time, I'm going to, let's see. All right. Yeah, so maybe I'll really quickly put out results. Oh, that's not the one. Yeah, OK. Yeah. So I'll just present my results and then conclude. So here we have our complexity listed both in terms of complexity and circuit depth, as well as the two different measurement schemes. For the leading precision dependency, we get what you expect on the top row for Heisenberg limited precision, and on the bottom row for shot noise, where you get 1 over epsilon squared, but you have the benefit of repeating and concluding your quantum calculations. We do get some logarithmic overhead as a result of this procedure. This comes from the need to have a certain level of precision in the data values. And finally, we get sort of the commutator lambda scaling. So lambda encodes some rather nasty commutator, but a commutator nonetheless, and our dependence on t being 1 + 1 over p, matching regular Trotter. OK. So I mentioned there's this result for Q-drift. Basic idea, everything stays the same. We just get the accuracy gains for time-evolved expectation values. So I encourage you to have a look at that if you're interested. And I think I'll conclude there. So thank you for your attention.
Thank you, Jacob. If I may, I have a question.
Sure.
So ultimately, do you end up doing either interpolation, or is it truly an extrapolation?
Right, yeah. So I realize the language there I've been a little confusing with, and it's because there's this common phrase, which is polynomial interpolation, but I've been trying to use more generally the phrase extrapolation to incorporate both the Richardson extrapolation technique, which takes only positive values of s and then extrapolates down to s = 0, and then also just to, maybe we can call it a polynomial extrapolation, but it does become an interpolation when we take the negative values of s, and sort of you can still think of it as trying to go from large values of s to small ones. So, but we analyze both of those methods rigorously in this work.
Thank you.
Hi, thanks for the great talk. Could you say a few words on the comparison between your work and multi-product formulas?
Oh, sure, yeah. I ran out of time pretty quickly, actually, so I was going to say something about that. So multi-product formulas are essentially a coherent Richardson extrapolation. So you're taking the product formula itself, and then you're using, let's say, a linear combination of unitaries to actually add the product formulas in linear combination, and that's going to cancel order by order. And essentially, the only difference here is we're saying, OK, well, we know at the end of the day we want the expectation value of an observable, so let's just do that Richardson extrapolation classically. And as you might expect, you save a lot of resources doing that. And this work is sort of rigorously showing that expectation.
Hey, Jacob, just an easy question for you. Have you solved the problem of how to do this with a time-dependent case yet?
I have not. That's still open. I think there's been some interesting work lately that has sort of used clock methods to sort of reduce to time-independent Hamiltonians, and perhaps then you could just port some of these results over. So I think there the question would be, if you can encode things in terms of a single accuracy parameters we've done here, then I suppose an extrapolation is always possible. So you just have to, I guess in principle it doesn't seem that algorithmically time dependent is any different because you still do have this step size. And then I think in our case, we just found the analysis a bit more complicated. Right?
And any progress on the Q-drift problem?
Yeah, so like I said, my collaborator James has put out this nice work on the archive for Q-drift, and I think in this case the actual operation is a quantum channel, which as you know makes things a lot more difficult. And James was able to sort of have a much easier time than we were thinking about this originally, because when we use this robustness result, we can then just say, OK, we're only going to take integer steps, and so we don't need fractional quantum channels. And that was able to pave the way for him to derive his results.
Question, can you do it with Lindbladian evolution as well, or is there some obstacles?
We don't analyze that in this work, but I guess in principle, I don't see why you couldn't. So if you did some sort of trotterization scheme with just Lindbladian operators and so on. In principle, this could work. So I think algorithmically this is extremely simple and versatile, and we chose a couple of problems that we felt we could very rigorously say something about, and hopefully that will, for those who are more on the practitioner side, there's no reason you couldn't really try to apply these methods to like a Lindbladian instead.
I think there's one last quick question. Let's see.
Thanks for the nice talk. What's the performance of these methods when subject to physical implementation errors? So for example, depolarizing noise that might be present even in error-corrected systems.
Yeah, that's a good question. So we did some very simple analysis in our work. And actually, I don't think it's yet on the archive, but it will be soon, updating this point. So in the case of physical noise, we did do a very simple model, basically like a depolarizing noise, or we basically imagined that something like for each per unit length, you have some error rate eta, where maybe you're decaying to some noisy value of the expectation value, and what happens there. And under that model, I mean, even though this method is not designed to handle hardware noise, you do benefit from the shorter circuit depths compared to Trotter alone. And with that you do get corresponding savings just from that. But even though this looks a lot like zero noise extrapolation for hardware error, it's not exactly that. We're basically doing something similar for Trotter error. So you get some savings, but it's sort of just from the efficiency of the method itself.
Okay, thank you so much, Jacob.